So, welcome back again, and I hope you all had a great weekend. I assume, is the audio okay in the audience? So you don't have any problems with that one. So I just wanted to give you a quick overview of what we are going to do this week. And you've probably seen the message which I sent. So we are going to start with a new topic, which is harmonic oscillations. And this is probably something which you may be a little bit familiar with, but it's a very important topic in physics, in mechanics. If you're going to the car industry, I mean, to understand harmonic oscillations is simply essential. If you want your car to be properly damped when it hits a bump, for instance. So, but harmonic oscillations play a very important role in basically all of physics. And we are going to look at on Wednesday on damping. So we will stay with this topic till slightly after spring break. And then you've probably seen that we placed the first midterm, and we put the deadline before spring break so that people have some spare time in spring break. That's the kind of idea. And what you will see is that many of the exercises, I don't know if you had time to look at it, but we are going to spend this Friday and also the next Friday on discussing the midterm. You can collaborate. You can hand in a common report if you want to. Remember just to upload the individual solutions, but you can always collaborate with your fellow students. And as you've probably seen, yeah.
How many groups can do one midterm? How many people can do one midterm together?
So typically 2 to 3 people is okay. You can be 4. That depends very much on you guys. So some people can work well together. And we had cases where the groups had to split up because they didn't agree with each other. That happens. But if you are fine with the 2 to 3, 4 people, that's fine. Because the kind of insights you get by discussing, they are really invaluable. As you probably have seen, there is a kind of repetition in all 3 exercises. And the thing we want you is to see from a plot of the potential energy that you can actually build up some kind of intuition and say, this is the way the system is going to behave. And based on that one, you can check whether that agrees with the calculations, whether the calculations are done by paper and pencil, or whether you run things numerically. So let me just give you an example before we move on to harmonic oscillations. And let's look at the potential which is given in exercise 3 or part 3. So let's take a small look at that one. And then I'm going to ask some questions to you and see if we can build up some kind of intuition about the motion by just watching the potential. Yeah. No, there's no homework, only midterm. We don't do homeworks and midterms in the same time, right? I mean, you are super fit people, but I guess you also have some limits, right? Okay. So let's take a quick look at one of the examples, which you have in the, not that one, but this one. So if you look at the last exercise, there is a potential. So this is the midterm. And I'm just going to show you the kind of example. And this is part 3. And we have a potential, which is in 1 dimension, which runs like -10 divided by x plus 3. So these are parameters which I just made up because it was easy to plot them in the kind of range of x values which I cooked up. And then there is another term which goes like r or x here. So one of the typical drills is to see whether this is an energy conserving potential or not. So that means you're going to calculate the curl of the potential. And you're going to do that with all the potentials which are listed in the exercises. Now, if you make a plot of this one, this potential is actually very special. So if we now make a plot of this v of x, and then we have x here, it's going to look something like this. This is a rough sketch. And then it goes like this. So this is actually what you're seeing here is a kind of a phenomenological mathematical model for the strong force. So the strong force, which never makes quarks break apart, that has something which is called confinement, and that's given by this X term. So that means that your potential now is going to actually trap a particle, and the particle will never escape. Because you have a part X, which just goes to infinity as X keeps increasing. So this is a typical type of potential which people built in the 70s and 80s and last millennium when they were trying to describe the interactions between quarks. So this X term is what drives confinement. Now, if you look at this type of potential, one of the things you're supposed to find is the minimum by taking the derivative, and that gives you the force. But suppose now that you are placed here, and at this point here, you have a zero velocity, and then you have a potential energy. So it means that V of X in this specific case is different from zero. So without having done any calculation, what kind of motion would you expect here? If I now let it go. Let me see. These guys always answer. So now maybe I should look after somebody else here, right? So I tend to say, I'm too close to these guys here, right? Any good suggestions? What kind of motion would you expect here? How is this object, if you place a particle at this point x0, so it has potential energy. Yeah, Jeremy?
Would it oscillate back and forth?
Yes.
Like via that level?
Exactly. So it's just going to oscillate back and forth. So it's going to oscillate from a distance x0, and then it's going to move till it has used up its velocity and it stops again. So energy is conserved here. So that means that the kind of motion you're going to have is a motion of the type, you will have this point here where you have the same energy. So let's call this an x1. So it's going to move back and forth in the well here. So that means that when you plot x as a function of time, you're going to get two extreme positions, x0 and x1. So you can actually, by just watching the potential itself, in this case, it's easy to see that the curl has to be zero. It depends only on the spatial degrees of freedom. So this is an energy conserving potential. So if you place yourself at x0, the energy which you have there, which in that case is potential energy because you gave an initial condition, then it's going to go to x1 till it has used up its kinetic energy and turned it into potential energy. And then it's just going to go back and forth. So this is actually this kind of motion which you see here. If you take away this x value, this x term, which gives a confinement, that is the kind of motion which the Earth is doing around the sun, except that x0 and x1 are very close to each other. So the orbit of the Earth is almost circular. If you take Mercury, on the other hand, that's clearly elliptical. So it's going to move between a minimal distance and a maximum distance between the sun and Mercury. And that applies to the other planets as well. So you can actually, from the graph, you already see what you might expect when you find the position and the velocity as the functions of time. And in a certain sense, the exercises which you're going to see, they're going to be a kind of repeats of this. So in the first exercise, there's a similar potential. And then we are going to go through all this drill by finding the local minima, the global minima. Is this a maximum? Is it a minimum? Is it a stable point or is it an unstable point? And so forth. So this is extremely useful, a kind of analysis to do because it's meant to build up your insight about the physics of the system. And this is a kind of analysis which you end up doing when you do physics. In many cases, somebody can even give you a parameterized potential. And based on that one, you can say something about how the system will behave. So since we now plotted this potential here, One of the reasons why I plotted it with this kind of shape here is that this kind of shape, which you see, is something you often encounter in many physics situations. It means that it looks like almost like a kind of x squared in the bottom. So what you can do now, if this object is just oscillating around the bottom here, you can think of making a Taylor expansion. If we make a Taylor expansion of the potential, one of the things which is interesting then is that we can derive the standard harmonic oscillator potential term. So that's actually based on a Taylor expansion around a minimum of the potential energy. So let's try to do that. So when we think of the harmonic oscillators of potential, this is actually based upon a Taylor expansion around the minimum of a potential well. And many potential wells in physics and in science in general, they have this kind of shape as you see here in the bottom. So what we're going to do now is simply to place ourselves at the minimum here and just make a Taylor expansion around it. So let's do that. And then we're going to get the harmonic oscillator. And that's the basis for harmonic oscillations, which we're going to study now, which is a very important field in physics. So I hope you don't get disappointed when you see that it's actually this kind of simple arguments which we are making. So we don't need to know the potential. So what we are doing now, when we look at the harmonic oscillator, so what you would have then is, suppose now that this point which we have, we just call this B, it's a distance B. And now we are expanding around this point B. So we take a V of X and do a Taylor expansion of V of X equal to B plus V of, oh, sorry, not that one, of X minus B. So this is just the us plugging in the Taylor expansion of D of X. And this is calculated at X equal to B. And then we have the higher order terms, which is X minus B squared of dV of dx, calculated X equal to B. And then we have higher order terms plus of O of X minus B squared, not cubed actually. So this is the Taylor expansion of the potential around the point B. Now, one of the things we notice is that we have now defined this around the minimum of the potential, right? So this B, this point which we have defined, V of X equal to B, is the minimum of the potential. Minimum of the potential. So if you now look at the equations here, what can you say about the second term in the Taylor expansion? The first term is just the value of the potential of X equal to B. But now if you take a look at the second term, which is the first derivative of the potential with respect to X. So what could you say about that value if you are placed at the minimum? That's 0. So we are at the minimum. So if you look at the plot of the potential here, since we have made an expansion around the minimum, then we can safely assume that the derivative, the first derivative, is 0, because we are at a minimum. It could be a maximum, but now we just stated that this is a minimum, and that means that that term is equal to 0. So what happens then is that you're left with a constant, the potential value of X equal to B, and then you have a second derivative, which goes like X minus B squared. So what we have now is the following. If we now skip higher order terms, we are now assuming that this potential is pretty smooth. Actually, there's a way you can make such potential in the lab. If you think of electromagnetic fields, you can set up something which are called quadrupole fields. A quadrupole field, an electric quadrupole field, goes like x squared plus y squared in 2 dimensions, multiplied with a constant. And that's a harmonic oscillator. And that's how people actually made something which is called a Penning trap, which gave the Nobel Prize in Physics in 1989, and which you can then use to trap ions in and perform high precision mass measurements. So you can actually set up electric fields so that you produce a potential which goes like x squared plus y squared in 2 dimensions. So if we now look at the value which we have here, so we have that at the minimum, then dV of respect to x, at x equal to b is equal to 0. And now we drop high order terms. And then we can set up an expression for v of x, which is equal to v calculated at b plus 1/2 times x minus b squared. And now we have the second derivative, which is calculated at x equal to b. So what we are going to say now is that this second derivative just takes a value. It's a constant. So we can now assume safely that at x, so this quantity here is actually the second derivative. We don't know the exact value. Like x equal to b is just equal to a constant which we call for k. So remember again that when you look at the function, you know that since this is a minimum, we know that this second derivative has to take a value. Should it be positive or should it be negative? It should be positive, right? This is a convex function, right? So that's the only thing we know now is that k should be larger than 0, because the way we plotted it is as a convex function. So this quantity k, from just a mathematical expression which we have, so this is quantity k, should actually be larger, or it could be equal to 0, we don't know that. But let's assume that it's larger than 0. And that's simply because we know that looking at the potential here, we have defined this to be a minimum. And since it is a minimum, then the second derivative has to be larger than 0. And it takes a value, right? See, if I give you a potential and you take the second derivative, that just gives you a scalar at a given value. So now we assume that this takes a constant, which we don't know the value of. If we do that, then you will now see that what we have is v of x, which is given by this constant, the potential at the minimum, plus 1/2 of x minus b squared, multiplied with a constant k. So if I now take the derivative of this quantity, then I have the force. So we know that the force, F of r, in our case, it's just f of x, because we are in 1 dimension. That's given by minus dv of d of x. And if I calculate the derivative, what this gives me, since v of b is a constant, we simply end up with minus, and then I have a half. So I end up with x minus b times k. And this is the kind of model which we get for a spring force. And this expression is valid around the minimum. And you know that if you have a spring and you stretch it, then you're actually stretching it away from its minimum. And then at a certain point, your spring is deformed and it loses all its elasticity, right? No more elasticity for the spring. And that means again that there is a limited validity of what you see here. And that's why we made this Taylor expansion around the minimum. And that's the same with a spring force. It has a limited validity because if you stretch the spring too much, it breaks. So this is how you would think of deriving a model for the standard harmonic oscillator force. And it's an oscillator because it's something which is going to oscillate back and forth when we look at the solution of it. That's why we call it oscillator. And it's harmonic because if you don't have any damping, it just behaves in a very harmonic way, right? That's the name harmonic oscillator. So let's take a look at the equations which we are going to get now. So we know that the force, and we are going now just to put B equal to 0, if that's okay. Just for simplicity, you can always redefine your origin, right? So now you can place the origin at B and just say that B is equal to 0. So that means that we have a model f of x, which simply is minus k times x. And this is equal to n times the second derivative of the position with respect to time. So that's the equation of motion. And we can now redefine it a little bit. So we are going to introduce a variable which we call omega 0. And this is given by the spring constant k divided by n. And this quantity here is now called, if you now look at a little bit carefully at it, so we know that the k, this variable k, has dimension. You remember from the beginning, we defined dimension by this kind of strange, how to say, mathematical symbol. So it has dimension energy divided by length squared, which again is equal to mass times length. So now I'm just setting in the units for energy in terms of mass and length, and time. So this is divided by time squared. And then I have to be careful because now I have another division here. So it's divided by length squared. So this has a dimension which goes like mass over time squared. If I then go back to the equation which I have and I ask myself, what is the dimension of this omega? Then I know that this is given by the square root of mass divided by time squared. And it's divided by mass again. And mass against mass goes away. So this has dimensionality 1 over time. So this is inverse time. And this is something which we normally call, in this specific context, we call it a natural frequency. It's a natural frequency because it's defined by the physical constants of the system. It's defined by the spring constant, which defines the system, and the mass of the object we are moving. So we call this a natural frequency. So there's a reason why I bring up this concept of a natural frequency. And that's because later we are going to look at what's called forced oscillations. So you could think of putting an engine on top of your object, which forces it to move at another frequency. So the ratio between the natural frequency and this forced frequency can make your system behave in an odd way. You can suddenly be jumping way too much. So if you can find an applied force with a given frequency, which resonates with the frequency of the system, this can often be a much gentler force which is applied to the system. So the natural frequency sets some constraints on the behavior of the system when you also apply an external force. And we will see that very clearly when we now are going to look at the applied external forces. We're also going to add damping to this system. So that means that as it moves on, it's going to lose velocity. So there's going to be a term which dampens the motion. And that's why you often would put on some kind of forced motion so the object can keep moving. If you look at the classical pendulum, which you will see in many places, that has an applied engine, so it moves back and forth continuously. If you were not to have this applied engine, it would come to a rest after some time. So these kind of motions are the kind of things we are going to analyze in the next 2 to 3 weeks. Okay, So let's look at the solution of this equation here. So the equation which we now are going to solve, if we now bring back this omega 0, so our first equation now is actually going to be given by the acceleration of dt, which is equal to minus omega squared times x. So this is the mathematical equation we are going to solve. Now, there's one thing I wanted to say before we move on here. So there are, I don't know how familiar you are with that. Sometimes when you are asked about the solution of a system, you can try different solutions and plug them in the differential equation. And if that gives you back the differential equation, you have found the solution. So in this course, we are not going to force you, except numerically, to find the paper and pencil solution of this, but we're going to give you the solution. And then you plug the solution back into the equation, and then you verify that this is the correct solution. So that's a pretty standard way of proceeding. So have you seen this kind of differential equation before? This is a famous equation in physics and science in general. So who has never seen it? Or rather, how many have seen it before? Okay, it's a good fraction. Do you know what the solution of this type of equation is? There are famous functions in mathematics. There are actually two famous functions. We can actually write it in terms of these two famous functions. Yeah? Yeah, sine and cosine. So this is why we get this kind of naming, harmonic oscillations, because the sine and cosine is going to give us something which just, in a very harmonic way, oscillates back and forth. Yeah.
I was going to add, I had seen this symbol before, but it was called the angular frequency.
Yes, that's called the angular frequency or the natural frequency. Exactly. This is excellent. This is also called the angular frequency. I called it the natural frequency, but I should have also added it's an angular frequency. Very good. Thanks. So let's, so the general solution, and let's then check that this is the solution. So this is a very common approach, and many people get confused because in some of the basic physics courses first, you will get the solution, and what you have to do then is to plug it into the differential equation and check that this is actually the solution. So let's do that. So we have a general solution of this problem, which is now going to be given by the following cosine and sines. So we have an x of t, which is given by an a times, this is a general solution of omega 0 times t, plus a b, so b and a and b are constants of sine omega 0 of t. Yeah. I have to get closer to here.
Are we not going to consider phase shift into our equations?
No, we are not going to do that. Right. So the we can also rewrite this in exponentials, in terms of exponentials, and we will see that a little bit later. But the thing is now that a and b, you have an infinity of values of a and b. And the way you determine them is by fixing the initial conditions. So you also have an infinity of initial conditions, right? You can start up here, you can start there, you can give it an initial velocity, you can give it zero velocity, and so on. So when you have specified initial condition, then you specify the final solution. So let's just specify the initial conditions and also see that this equation here is the solution. So if we now take the derivative of this quantity, we should get the velocity, right? And if we take the second derivative, we should get back to the differential equation. So let's see that we get the differential equation. So let's take the first derivative and just check that we get the velocity. So we know that the velocity is given by dx dt. And that means that we get minus a times omega 0. And then we have a sine omega 0 of t. And then we get plus b times omega 0 of cosine of omega 0 of t. So I'm just taking the derivative. So that's going to be the velocity. Now, when you compute this numerically, you can actually check this against your analytical solution. Then if we take the second derivative, we should get back to the acceleration. So if we take dx dt, second derivative, this gives us minus a, but now we get an omega squared times cosine omega 0 of t minus, and then we have a b of omega squared times sine of omega 0 of t. And if we look at this one, this is if we put minus omega 0 squared outside, then we have a times cosine omega 0 of t plus b times sine of omega 0 of t. And this is nothing but where we started. So what we have shown here is that this is actually the differential equation where we started. So this is another way of finding the solution. So if you guess on the solution of a cosine and sine, you can plug that into the differential equation. And if it agrees, then you have shown that this is a solution. So there is no need to, you can solve these differential equations by paper and pencil, but not everybody here has actually done that in math classes. And it's pretty common in the first physics courses to actually just do this kind of a proof by plugging in the solution and showing that that gives you the differential equation you started with. Now we have an infinity of solutions due to the constants a and b. So what we need to do now is to specify the initial conditions. So if we specify x at time t0, we just call this x0, and then we would specify v at time t0 equal to v0. And let's, for simplicity, just assume that it has 0 velocity in the beginning, okay? So if we now look at my solution at x of t0, and now I'm going to say that t0, for simplicity again, is equal to 0, okay? So that means that what I have then is that this is equal to x0, and this is a times cosine of 0 plus b times sine of 0. And we know that sine of 0 is 0 and cosine of 0 is 1. So this is just 1, this is 0. So that means that x0 is equal to a. So that's one thing. So we haven't been able to define b because b disappeared since sine of 0 is 0. So sine of 0 is 0, so that means that b could take any value. So let's find b. So what we need to do next is to go back and look at the velocity, dx of dt, and we calculate this one at t0. So this is the velocity at t0, and we require that that one is equal to 0. So that's the initial velocity, right? So if we plug this one into the equation for the velocity, if we go up a little bit, we have the equation here. So that's minus a times omega 0 times sine. So that means that we have minus a omega 0 times sine of omega 0 of t0. And then we have plus b of omega 0 times cosine of omega 0 of t0. Now, what can you say about the value of b now in order to satisfy the initial velocity to be equal to 0? So the first term is obviously 0. A is different from 0, but we have a sine, which gives us 0. But then we have a value, so I should actually put this up so you can see it properly. So if you look at the value for b now, what should b be like in order to fulfill the initial condition? Yes, because that's the only way, because cosine of 0 is 1. omega 0 is assumed to be different from 0. So in order for this one to be correct, then b has to be equal to 0. So now we have the initial conditions which have been used to determine the explicit shape of the function. So this means that b has to be equal to 0. And if we plug that in, then we have the final solution, which says that x of t is equal to x0 times cosine omega 0 times t. And that's the final solution for the equation here. So in our case now, with the initial conditions, we have been able to find the explicit form for the solution. Now, there's something else. If you notice this function here, what happens when I've gone a full cycle, an angle of 2 pi? So if I now put in, suppose I take a time, let's put that one. If I now say that time is equal to 2 pi divided by omega 0, what happens with the solution then? Any good suggestions? Yeah, I say again. No, this, if you plug in 2 pi divided by omega 0, and then you continue after that. So what happens? Yeah.
Would you be back at your initial position?
Exactly. You repeat yourself. This is just, as I said, like me, I just keep repeating myself. So this function here is actually called the period. So that's the period of the solution. So when you have gone a time, which corresponds to the period, you're back to the same position. And then you repeat yourself. So I invite you to find my period. According to my daughter, my period is just a few seconds before I start repeating myself. Actually, I'm portraying them as people who always tease me. They do tease me, and I deserve it, but they're very kind, actually. Okay, so this function here, when you have done this, this is normally called the period. And we would put a specific label to it, so a tau. And then the solution, you're back to where you started, and then you keep repeating. So you get this kind of harmonic oscillations back and forth. So if you look at the potential we started with in the very beginning, this potential up here, if this was a pure harmonic oscillator, it would just repeat itself back and forth. And then you would come back to the positions x1 and x0, and then you would just see the same kind of repetitive motion all the way for an infinite time, unless you put on some kind of damping to the system, and then it will come to rest. So you can get a lot of kind of interesting interpretations by just looking at these simple equations here. So I just have to remind, yeah, so now let's look at another thing. One thing which we can show now is energy conservation. So let's look at that within the same model which we developed here. And when you're looking at the midterm, these are the kinds of arguments which you need to make in order to show energy conservation. So many of the things which we are talking about now and which you have seen before, they transfer immediately to the way you will reason when you're solving the midterm. So if we now take the next topic, which is energy conservation. So this harmonic oscillator, and we showed that earlier, that has a curl which is equal to 0, which means that it's an energy conserving force. So in our case, we have E, the energy is given by the kinetic energy plus the potential energy, which in our case is the harmonic oscillator with kx squared. We are still in one dimension. We found that V0, this is our initial condition, is 0. And then we defined that x at t0, the initial time, is given by x0. We found that the solution then, x of t, was given by x0 times cosine of omega 0 times t. This is a general solution at a time, and now we can look at a time t different from 0. So at t different from 0, we have an energy which will now depend on the velocity at this specific time of t plus the position at a time t. So this is the energy of the system. And we are claiming now that energy is conserved. So when we go to a time t equal to 0, at t0, then since the kinetic energy is 0, what we have then is that the energy at t0, which we are going to call E0, is simply given by 1/2 of k. The velocity is set to 0, the initial velocity, and then we simply have x0 squared. That's our initial energy. And this is like the kind of situation which we started the discussion in the lecture today. We started with an object which was at rest, and then it started to move down in the potential web. Now, if we do that, we know that E of t should be equal, if energy is conserved as a function of time, then we should have that this is equal to E0. Now, if we now plug in here, we have the solution. So we know that E of t is given by 1/2 of k times x0 squared. And then I have the solution here, which is a cosine squared of omega 0 t. If we now go back to the velocity, we know that v is given by dx dt, which in our case is the same as minus x squared, as x times omega squared, and multiplied with sine of omega 0 of t. So this is a small digression here. It means that we need to add the velocity, which is now 1/2 of m, and then I have the velocity squared. So I get x0 squared, omega 0 squared, and then I have a sine squared of omega 0 of t. Now, what I also know is the following. So in my case, I know that this omega 0 is the same, or squared, is the same as k divided by m. So I can now take these values, which you have here, and plug them in here. So if I do that, what I get then is the following. So I get that this is equal to 1/2, and then mass disappears because I have a mass term here and a mass term here, so that disappears. So I get k times x0, no, not x, not that way. I get x0 squared, like this, and then I have a cosine squared of omega 0 squared times t, plus a sine squared of omega times t. And this is obviously equal to 1, right? Famous relation for the cosines and sines. So these, and that gives us simply now 1/2 of k times x0, which is actually equal to E0. So we have shown now with the solution we plugged in that energy is conserved. So in the midterm, when your program is functioning properly, one of the things you can check then is to plug in the expressions for the kinetic energy and the potential energy, because you have x and v, and then you can calculate kinetic energy and potential energy, and then you can study whether the total energy is conserved as a function of time. That's an extremely useful test, and you will then see that a method like Euler's method does not conserve energy. And you need actually to do this small trick, which we did last week in homework number 5, to add this Euler-Kromer addition to the solution. And then you will conserve energy. So these are extremely important tests to make when you do it either by paper and pencil, like we did here, or if you have a functioning program, you can easily test whether energy is conserved or not. So these are things which you will see which we as physicists, these are things which we keep doing all the time. If you have an energy conserving force, it's very important to actually check that your code or your paper and pencil solutions do conserve energy. So these are things which you will always be asked. Does your algorithm, does your approach conserve the energy because you have an energy conserving force? And it's a very useful test of what we are doing. Okay, so what we are going to do now is to look at another example where we can get something which looks like a harmonic oscillation. There is a famous, should I say infamous system, which you have seen many, many times before, which leads to harmonic oscillators if we have a small angle. Does that ring a bell? Something which oscillates with a small angle? Pendulum, right. Now, the thing which is nice is that you can actually, we are going to set up the full expression where you have a sine function in there. And that's something which normally does not lead, unless you have some specific conditions, which leads to an analytic solution where you actually have to solve things numerically. If you take a very small angle, it's going to be a lookalike of the equation which we had here for the harmonic oscillator. So have you seen this equation being derived for the pendulum without this small angle approximation? So what we are going to do now is just to repeat a little bit of these things and derive the equations. And that's always useful to do, because then you will just see another applications of these harmonic oscillations around some kind of a small value. Now with a pendulum, you can actually set up a angle which is large, and then you would have to have a sine term in it. So from a paper and pencil point of view, this is a painful thing to solve analytically. Numerically, it's just one line of code where you replace the acceleration and you add a sine term in the acceleration. That's the only thing you need to do when you do it numerically. Okay, so let's look at the pendulum. And just let's set up the system, which we are going to study a little bit more on Wednesday. So we have an example, and this is normally called a mathematical pendulum. So we're going to look at the system in 2 dimensions. So we have some kind of roof here where the pendulum is fastened to. So this is my X direction, and then I have my Y direction here. And now I have a pendulum here, which is kind of has a rigid rod like this. It has a mass here. There is the gravitational force which acts on it. So this again is us analyzing the problem. It has a length which is fixed, so it doesn't change the length. So you could make this more complicated, and I hated these exercises, really. So I remember when I did mechanics, we had these coupled pendulums and they could vibrate and so on, and it was just a nightmare. When you write a code for it, it's just a few lines because you just have the forces and you just find the acceleration. But when you do it by paper and pencil, it's guaranteed a nightmare. But let's take the simplest case. And it has an angle phi here. And this is where we're going to start on Wednesday. But let me just try to set up the system. So there is a distance to the mass here, which we call for r. And this length is fixed to be equal to r. So this is a definition of the system. And then there is some kind of tension here, some force which acts along this rod, which we're just going to call for T here. So these are the forces. And then we're going to break the forces in X and Y directions. And then when we have the forces in the X and the Y direction, we can find the acceleration in the X and the Y direction. And when we have the accelerations in the X and the Y directions, we can try to see if we can simplify these equations. So the equation we are going to find here is this equation here. This is the standard equation for the pendulum of the angle as a function of time, which is given minus g divided by the length times a sine of phi. You've probably seen that equation, right? So we're going to derive that one on Wednesday. And then you can make the small angle approximation. So if phi is much, much smaller than 1, then this looks like a harmonic oscillator. And this is going to give us the standard sine solutions here, minus g divided by L times phi. And the natural frequency, or the angular frequency in this case, is going to be given by the square root of g over L. And now it's time to stop. I've abused a little bit. I went 1 minute over time. I hope you can forgive me for that. So let's